Hi, welcome to Analog Layout and Design, and today we are going to discuss about MOSFET capacitances. Okay, today we are going to discuss about MOSFET capacitances, and what you see over here is the cross section of a N MOSFET. Okay, there are various capacitances available. Like first one is the oxide capacitance. What you see over here, it is the oxide capacitance. So that forms between like this is the gate, this is the drain, and this is the source. Okay, so oxide capacitance forms between the gate and the channel. Okay, so that is the oxide capacitance C1. Then we also have a depletion capacitance C2 here, so that's what is shown here. And then we have like the overlap capacitance. See, strictly speaking, the drain should have been only so much, should have been like this, and the source should have been only so much, but then there is like a overlap here, and that's why we have like C3 and C4, which is like the source overlap capacitance and drain overlap capacitance. Then we have like this is the source and drain, this is the source and drain region, and they will have some, and this is the bulk, so they have some junction capacitance, so we look into that one also in detail. Okay, so these are the different capacitances that are available in the MOSFET, which we will look in detail. So before understanding the capacitances, first let's try to understand like how the MOSFET looks like. Okay, so this what you see here is the gate. Okay, so this one what you see here is the drain, and this one what you see here is the source, and this pink thing is nothing but the substrate. Okay, now whenever I give some gate voltage at some voltage at the gate, this channel, there will be an inversion layer here. Okay, and that would be that is what is shown as the N channel. Okay, and that is nothing but the P substrate which is inverted, which will be like N type material now. Okay, so if I zoom in only this portion, that's how it looks like here. Okay, so this is the gate, and this is the drain, and this is the source, and this will be the channel here. Okay, and that's the front view. If I see from here, that is the front view, that is the, this is the gate here. So this one is the gate, this one is the gate oxide, and this one is the substrate. So this is the substrate connection, this is the gate connection. Okay, now if I see this one, this, if it has some charges like this, and if this has some charges like this, and in between if I have a insulator like this resembles a capacitor. Okay, so that is nothing but my oxide capacitance. So this oxide capacitance has a different behavior. It will not be always the same. Based on the gate voltage, it will change. Okay, how will it change? We'll look into that one. Okay, so let's try to understand oxide capacitance in detail. So the oxide capacitance actually is a function of like the gate voltage. So based on the gate voltage, the capacitance will change. What do you mean by capacitance? Capacitance is nothing but how much charge it can hold. Okay, so suppose say this is the insulator, this is one plate and other plate. How much charge it can hold in these two plates, that is nothing but your capacitance. Capacitance is nothing but the capacity to hold the charge, that is your capacitance. Okay, so we, as I told you, we have three different types of regions in which the capacitance will vary based on the gate voltage. Substrate is connected to ground, and if V gate is negative. Okay, so suppose I have this gate here, I connect like this, and I give minus 2 volt here. So the gate applied voltage is minus 2 volt. That time what happens is this is negative, so your negative charges are here. And substrate is P type substrate, So which has holes or the positive charges here. All the positive charges come and accumulate at this oxide. This is the oxide interface, and here what is known as this the capacitance. So this is the negative plate, this is the positive plate, and this is the insulator. A capacitance gets formed, that is the oxide capacitance in when the Vg is negative, and that is called as accumulation. So this is the accumulation region. The same thing is shown in this graph here. Okay, so this region is negative voltage, and this COX what you see here is the value of this capacitance, oxide capacitance, which is a higher value. Okay, it is there till here. So now I keep reducing this voltage. What happens when the voltage reduces, the electric field decreases, the electric field whatever was there, that decreases, and the charge holding capacity will reduce. So here you will not have so many positive charges, all of them start going away, and then what happens is that this reduces. So what is happening here, there is no positive charge here at all, so it's like no charges at all. So that's when it enters what is known as depletion region. Okay, so then it is divide of all the charges, and then it is called as depletion region. What you see here in this graph is that one only. When the voltage goes on reducing, okay, or it is going towards zero, so this is the zero, and below this voltage, if it reduces up to certain voltage, it will be in accumulation region, and there is one voltage known as the V flat band voltage. When it reduces less than the flat band voltage, then the charges go on reducing here, and that is when it is called as the depletion region. So here there is no charge at all, so there is no capacitance at all, it is very little capacitance here. So the capacitance reduced because the charges are not there, and the voltage is also not there to have a strong electric field. So this is known as the depletion region. Okay, so now what I do, I start giving voltage greater than 0. Okay, so now it is like depletion is over, then I start giving positive voltage which is greater than 0. In positive voltage we have two different regions. In negative voltage we had two different regions, one is the accumulation and a depletion, and in positive this one we have what is known as the weak inversion and strong inversion. So in weak inversion what happens, very little charges are there, so there is no like strong this one, this is also depletion only, and very little charges will come. Then what happens is this channel starts getting inverted. So here this is plus and I want like minus here, so one or two negative charges will start coming, and finally when the voltage crosses what is known as the VTH or the threshold voltage, then I have like a proper channel formed here which is totally negative, and this is positive. So I have a strong inversion here, and this is the capacitance which is in strong inversion region. So again the same voltage or the same capacitance is there which is COX. So in depletion region it reduced, and in inversion weak inversion region it started increasing. Again the same gate oxide capacitance will come. So in between this region we can use this as a variable cap, but generally we will not use. Okay, in this region we can use it as variable cap. In this region we can use it as a variable cap. But here I have to apply a negative voltage. So we will not use it in this region as a variable cap. But in this region we can definitely use it as a variable cap because it is varying with respect to the gate voltage. So this is a variable cap. After that it is fixed. In strong inversion it is fixed. In accumulation it is fixed. Okay. So generally we will use normally in this region we will be using MOSFET as a cap. So in strong inversion and weak inversion when the gate voltage is positive. So most importantly what we should see is in this when it is in accumulation region, so this is negative and this is positive. and in inversion region it is positive and this is negative, but the capacitances are same. So here also the capacitance is same, here also it is same. So when it becomes like when the voltage makes a transformation from negative to positive, so this is negative and this one is positive. So in between when it makes a transition, it will enter like a depletion region first. After that, it will enter inversion region. In both these regions, the oxide capacitance will vary. Hope the oxide capacitance is clear. Okay. Strictly speaking, I should have my capacitance like this, MOSFET like this. Okay, this is the gate. What I have. This is the drain and source. So between gate and drain, is there any overlap? There is no overlap. Gate is here, gate ends here, and source and drain happens here. Because of the manufacturing process, what happens is this one will go a little more on the both sides. Okay, so now this is my drain and source, and this is my drain. It won't get formed within that limit. It will go a little more inside the under the gate. So that's what you see here. Okay, so this is the gate. Under the gate I have my source, and under the gate I have my drain. So this one looks like this is like N. Okay, this is the negative, and this portion whatever you see here, here it is the positive. This portion what you see here, so this is the negative and this is the positive, and in between what I have oxide insulator. So these two will look like capacitances. So that is what is your gate to source overlap capacitance. Similarly, we have gate to drain overlap capacitance. So you would have seen in circuits like this, I have MOSFET like this, I have this is the gate, they will show a capacitance like this CGD, and they will show a capacitance between gate and source, this is CGS. These are the capacitances which are parasitic capacitances formed because of the structure like this. So drain should have ideally, source and drain should have ideally been only so much. Now there is a protrusion under the gate area. Because of that there is a overlap capacitance, that is your CGD and CGS. Okay, so here I have written down the MOSFET. So we have one more thing what is known as the junction capacitance. Okay, so this what you see here is the top view. This is the gate, this is the source, and this is the drain. Okay, so this region whatever you see, this is the top view, and this same thing I have written down like this. So this is how it looks like. And what is this? E is the length of this guy, so that's what is this E, and width of this guy is nothing but width of the transistor W. Okay, so this will also be W. Okay, so same thing I have drawn here, and we have what is known as the junction capacitance. We'll look into that one in detail. So if you see, this will be something like this, right? It will be something like this. Okay, okay, so this is the top surface, this is the bottom surface, and these are the side surfaces or side walls, I will call it. Four side surfaces are there, top surface and bottom surface. So here it is all inside the substrate, P minus substrate. Okay, so now we'll have something in the top. What you have? Top you have contacts, and then it will go to metal. In the top surface I don't have any capacitance. In the top surface I don't have any capacitance. Okay, so now I have this. If you see this way, so this bottom surface will have this area, and bottom surface with substrate, P substrate. What is this material? So this is the N plus, right? And what is substrate? It is P type. So this and this will form like a P PN junction, which is reverse biased. So whenever you have PN junction, there will be a depletion region in this region. Okay, there will be a depletion region, and that depletion region will have some capacitance. So how will that look like? This is the P, this is the substrate. In between I have no charge. So depletion region, that will form like a insulator. This is N, this is P. In between I have depletion region which will act like a insulator, and I will have like a capacitance. So that is this bottom plate capacitance. That is your bottom plate capacitance. We always know, if I know one unit capacitance, right? Say 1 micrometer by 1 micrometer. If I know the capacitance, if I have to calculate for say some 5 micrometer by 10 micrometer, what I do is I will take this capacitance and multiply with the area. Okay, so 10 micro by 5 micro is the area. I will just multiply this unit capacitance with this. So I will get that capacitance value. Suppose say this capacitance here, this value is C junction. Okay, so I told you it's not on the top plate, it is at the bottom plate. Bottom plate we have what is known as the junction capacitance. The unit value is Cj. Then how do I multiply to get the full value? So this is nothing but width and this is nothing but E. So I have this is the bottom plate which has got like length of E and width of W. I have to just multiply with the area. E into W, I will multiply by Cj. That's my total capacitance. Okay, so we understand that in this one we have bottom plate. Bottom plate will have a capacitance. Not only on that, not only that, no, even the side walls will have capacitance, right? So if I have a junction like this, the drain region like this. So bottom we understood. These are the side walls, right? Four side walls, all of them will have capacitance, because what you see here is also substrate. Okay, all four sides we have substrate only in the top we don't have substrate. We have like these contacts, and then it will go to metal one. Top we don't have any capacitance, but side walls will have like capacitance. So what is the capacitance of these guys, all four regions? Okay, this thickness will be very small, very small. Okay, area is what actually this E into thickness, right? E into thickness is the area of this one side. E into thickness, and this side it is. So if I write it like this, so this is E and this is W. Okay, and this is the thickness. So what is the area of this front face and the back face? It will be the same, right? Front and back. This is the back face and this is the front face. So what is the area of this front? E into T. But if thickness is very small, I can just ignore T and I will simply write the area as, instead of E into T, I will just write it as E. So back also it is the same thing. It is E. And here also the thickness is very small. What is the area? I can simply say, instead of W into T, I will just write it as W. So here also it is W. So what is the total area of this guy now? This is E and this is W. So here also E, here also E, here also W, here also W. So it is 2 times E plus 2 times W, or 2 into E into W. And if I know the capacitance of small area, I have to just multiply with this. So I will get the capacitance. And this one is known as the side wall capacitance. So the unit one will be Cj side wall into 2 into E plus 2 W is the capacitance. Okay, so this is the total capacitance of side wall. So in junction capacitance, what we have? We have two types of capacitance. One is the bottom plate, one is the side wall. Two types of junction capacitances. Hope this is clear. Okay, we'll try to summarize the different capacitances that we discussed. First one is the oxide capacitance, which we discussed. So that's between the gate and the substrate. So we have three different regions in this one. So in this oxide capacitance, so we saw that the variation like this. So based on the V gate, okay, if it is negative, it is like a accumulation, and if it is positive, then it is inversion. And once the voltage reduces lesser than V flat band, so or it increases more than V flat band, we have what is known as the depletion region. And then once it goes more than 0 and less than VTH, so that time it is called as the weak inversion. And this is how it varies, the oxide capacitance. It is not the same all the time. And then we discussed about the overlap capacitances. Here ideally the drain should have been only so much, but then there is like a protrusion under the gate, so that's why we have like the overlap capacitances between the gate and the source and gate and the drain, which normally we will show it like this, as like the CGS and CGD, sorry, and this is the CGS. So that's about the overlap capacitance. This one we didn't discuss much, that's fine. And source and bulk junction capacitance. So we understood that the entire, so if I see the source or drain, it will be something like this. Inside the substrate we have what is known as the bottom plate capacitance, that is nothing but C junction, because that one is like this is N plus and substrate is P. We have what is known as the PN junction, and in PN junction we'll have a depletion region, and that's how we get a capacitance in between the P and N, and that is your junction capacitance. And if I know the unit value Cj, then I just have to multiply by the area. Area is nothing but E and W, so that is nothing but Cj into E into W. This is a big capacitance actually. And then in this one more portion is there, that is nothing but your sidewall capacitance. So the bottom plate capacitance we understood, and we have like 4 sidewalls. And if I know the unit capacitance, so I just have to multiply by the parameter. So if this is E and this is W, so 2 times E and 2 times W is the perimeter, and the unit is Cj sidewall. So then I will get the sidewall capacitance. So this, and along with the bottom plate capacitance, which is nothing but Cj into E plus E into W. So that is the total junction capacitance for both source and drain. And this one is generally represented as C drain bulk, C dB, and C source bulk, CDB. Okay, so if you see the MOSFET, so normally we have all these capacitances. So this is the source bulk, this is the CDB, which is the junction capacitances, and we have what is known as the CGD and CGS, which are the overlap capacitances. Oxide capacitance is between the gate and this one. Oxide and depletion capacitance is between gate and substrate. So hope the capacitances are clear. So hope you enjoyed the video, and please hit the like button and don't forget to share and subscribe.